Hello and welcome back. We just finished learning about curve evolution. There's one thing that is missing that we need to learn is how do we implement curve evolution in the computer. We saw that curve evolution is important, for example, to regularize curves with curvature motion, but even more important for active contours. And we need to learn how do we implement in a friendly fashion that in a computer we have discrete images, so we need to talk about the numerical implementation of that. One of the areas that has had a tremendous impact in image processing, in particular when we talk about PDEs in image processing, is level sets methods, and I want to explain that. And with that, we are going to know how we implement any type of curve or surface evolution in a computer. So what is all this theory, all this framework of level sets? So we have talked about curves, and it's going to be the same for surfaces, but it's much easier to present this for curves. We have talked about curves and curve representations, and we see that here we have a curve that is parameterized, and remember, for every p, we have basically a different point on the curve. Now, this is not the only way to represent curves. There's a very different way to represent exactly the same curve that is actually even more familiar when we are talking about shapes. And the basic idea is that instead of parameterizing the curve, we're going to represent the curve by all the points on the plane that hold a certain equation equal to 0. So let's look at this figure. We're going to put a coordinate system, x and y, and then we say every point in the curve is a point such that phi at that point is equal to 0. So we have to define this function phi. And for example, we can define the function to be positive inside and negative outside. And one example is to define that as the distance to the curve. For of course, the distance to the curve at the curve itself is 0. The distance to the point itself is 0. So every point on the curve has 0 distance to the curve. Every point inside has a positive distance, and we define every point outside to be a negative distance. In that way, we define a function phi that the 0 set, that's called the 0 level set of that function, meaning all the points on the plane where that function is 0 define a curve. Let's look at a profile of this, and we see that here. If I have a function that is positive inside and negative outside, and I cross it with a line, then this is the profile. We are going from negative to positive, so this region is positive. Then we go again outside, so we have negative again, and we go again inside, and we go again outside. Now, which are the points that belong to the curve? This point, basically the 0, this point, and this point. Every time the profile of phi crosses the 0, that point belongs to the surface. In that way, belongs to the curve, or a surface if we are in higher dimensions. In that case, in that form, we are defining a curve on the plane by all the points that hold this equal to 0. And these two are just two different representations of exactly the same curve. This is kind of painting inside the curve and painting outside the curve in such a way that along the curve that paint is equal to 0. Now, with this representation, we have computed tangents, normals, and curvature. We need to be able to compute it with this representation, otherwise we won't be able to do curve evolution. So let's see how we do that. And we're going to prove a couple of things. As we have talked, this week is one of the most theoretical ones, but we're doing everything self-contained, so I'm explaining everything inside, and I think we're learning a lot of new concepts. So let us show that basically, if we define the curve as before, as the 0 level set of the function phi, the normal is the gradient of phi divided by the magnitude, actually with a minus. That's a convention because I want the normal to point inwards. It's just a convention. And of course, the tangent will be this. It's basically a perpendicular vector. Let's prove that. It's not hard to prove. So remember, we have the function phi, and all the points that belong to the curve is where phi is equal to 0. So along the curve, phi is not changing. It's always 0. When I travel the curve, it's always 0. Then the derivative of the function along the curve, along the arc length, because I'm traveling along the curve, is equal to 0. Let's compute that derivative. So I want to take the derivative of this function. Remember, the function exists all over the plane, and I'm taking the derivative in the direction of the curve with the arc length along the curve. Now, we have it here. This is just the chain rule, basic calculus. So if I have to take the derivative according to s, it's the derivative according to x, x according to s, and the same for the y. So that's simple calculus. Now, what I wrote here is this inner product. Remember, the inner product of two vectors, so I'm going to write it here in case you don't remember. If I want to multiply two vectors, a, b, I want to do the inner product, let's say with c, d, is a times c plus b times d. So this is nothing else than the inner product of the gradient of phi with the tangent. Remember, xs, ys is the tangent, is the unit tangent. We saw that a couple of videos ago when we were talking about differential geometry of curves on the plane. And phi x, phi y is just the gradient. So this is what we have here. Now, this is 0. Okay, we have it here. Of course, this is the 0, so I'm gonna go here. And of course, I'm allowed to normalize. So here I have proof that the gradient of the curve is perpendicular to the tangent. Then I normalize the gradient. So if I have a vector that is perpendicular to another, of course, any change in magnitude in the vector is still perpendicular. In particular, I want to basically normalize it to have unit norm. And then I get this equal to 0. So if this is perpendicular to the tangent, then this is the normal. So I have a perpendicular, this is the normal. And now once again, we as a convention put the minus because we want, if we have positive and negative, we want the gradient to point basically, we want the normal to point inwards. Once again, it's just a convention. So a very simple proof that basically shows that this is the definition of the normal. So having phi, I can compute the normal with absolutely no problem. And of course, I can compute the tangent, just the perpendicular vector to it. And we have the first, actually we have two, the normal and the tangent. Now let us compute the curvature. And again, a very simple computation as we have here. Just maybe two more steps and we get the curvature. So what we want to show is that the curvature, I only have phi. Remember, the curvature is the second derivative according to s. So the curvature was CSS equal Kn. That's a curvature. This is I want to compute. I don't have C. I have phi. I have C, the curve defined implicitly by phi as its zero level set. And I want to prove that is this formula. In case you don't remember what div is a divergence. And the divergence of a vector alpha beta is basically alpha x plus beta y. So it's a scalar. The first term of the vector, you take the derivative according to the first coordinate x, the second according to the second coordinate. Okay? Let us prove this formula right now. So now we are still going along the zero level set. So we still have this relationship and let's just exploit it now. We're going to compute the second derivative of phi along the curve with arc length. We just compute the first one in the previous slide when we're computing the normal. Now I want to compute the second derivative. So I have the first derivative and I want to take one more derivative. Now once again, this was nothing else than the gradient inner product with t, as we saw the previous one, and I have to take a derivative. Remember, derivative of a inner product is derivative of the first times the second plus the first times derivative of the second. Now, what's the derivative of the tangent? Second derivative is curvature in the normal direction. So here it is, curvature in the normal direction. So once again, derivative of the first one times inner product with the tangent, and then the first one inner product with the derivative of the second one, which is t, but we know that the derivative of t is kn. And this basically is equal to 0. So what we have, so this is equal to 0. So what we have is that this term is equal to minus this term. And basically I wrote that here. So this term, I can take the curvature outside. Okay? That's not a problem. It's a scalar. I can take it outside of the inner product. That's the first thing we do. Oh, I apologize. There is here a typo. This should be a phi. Basically a kind of a capital phi. But I apologize for that typo. We are going to continue. It's just very easy to see that going from here. I just made a typo. And we basically have the curvature goes outside. That's here. Then we have this again here. And the normal, we just saw in the previous slide, is gradient divided by gradient. So we have curvature here. Now this product is the gradient square, because I'm multiplying this by itself. So it's the gradient square divided by the gradient. They cancel each other and I get only one gradient. So this term is here. Okay? This term, I'm not going to write it down, but by now you're an expert because we're just doing derivatives and chain rule. If you want to take the derivative of the gradient according to s, remember you have to take the derivative according to x, and then xs plus derivative according to y, ys. So you do chain rule again, and then you're going to get this expression. This expression is basically this derivative, and then the tangent, once again, we have from the previous one. Now, we got this equality here. If you now open this with this definition, you're going to see that it's identical to here, times this. And then we got basically the formula for the curvature of a curve that is represented in implicit form. Now, pay attention, this is extremely important. It's going to be very important next when I explain the forming curves in level sets. I don't need to have the curve. I don't know C. C is in implicit fashion defined. All I need to know is phi, and I take regular derivatives in the x direction, in the y direction. We know how to do that. So this is the x direction, this is the y direction. We know, we just take the derivatives as we have been seeing many times in this class. This pixel minus this pixel, or this pixel minus this pixel when we are taking derivatives in the y direction. And we do that a number of times just following this formula, and we get the curvature, or we get the normal, or we get the tangent. So it's much simpler. I don't have to go and take derivatives along the curve. I take derivatives in the grid, basically in the image. Really, really much simpler. So now we know the curvature, we know the normals. Do we know how to deform curves? Let's see about that. So the next step is to learn how to deform a curve, how to deform phi in such a way that the boundary basically is deforming as I want it. So we have a function that is representing a curve in implicit form. Okay? We know that the curve that is defined in this way it's moving with this velocity. And we ask ourselves, how do I have to change phi for the level set of phi to move according to this velocity? And it turns out that it's this formula. And I'm going to prove to you here in just a couple of lines. But before we do that, please pay attention to what's happening here. The phi is, once again, it lives on the image. It lives on the grid. Every time I'm talking about derivatives, I'm talking about derivatives on the grid. So the pixels are moving up or down. There's no derivatives on the curve, which are very difficult to implement. This is like when we have seen how to compute a gradient. Again, this minus this. We have seen those things. So implementing this is much easier than implementing this. Let us prove this formula. So the basic idea is, once again, very, very simple. I'm going to take the derivative of phi according to t, okay? And this is where I'm going. I'm going to take the derivative according to t of this side and the derivative according to t of this side. Now this side is 0, it's a constant. So the derivative on this side is also 0. Here it is. The derivative here, I wrote it here. And now, once again, chain rule. And this is what we have. The derivative of this function of x, y, t according to t is what I have written here. So I take the derivatives according to x, then xt plus derivative according to y, yt plus derivative according to t. These are partial derivatives. So this is what I have, okay? Now, this I move to the other side because I have a 0 here, and I get minus the derivative according to t equal to the right hand. So this part is equal to minus this. This we have seen before, okay? Is an inner product, as we have seen already at least 2 times in the previous slides. So it's the gradient of phi because of this part, and this xt, yt is ct, is basically my curve deforming. So we are here now, we have one more step. Ct, I know what it is, Vn, so I write Vn. It's the motion of my curve, exactly what I want. So once again the V can come out because it's a scalar, and I have this. Now remember, I want to write everything as a function of phi. That's the important part, okay? So we just saw that the normal is minus the gradient normalized, okay? So here we basically plug that. We replace minus the normal by the gradient of phi normalized, okay? And this, as before, is gradient times gradient, that's gradient squared, divided one gradient, we get one gradient. So this is gradient, V stays, and we got this, and because there is a minus here, it cancels with the minus here, and then we have that this is equal to this, which is what we wanted to prove. Okay? So once again, you can look at this. If you wanna, you can pause the video now and look at the proof. There is nothing here but applying the chain rule and then writing everything as a function of phi. That's the important part. We get that when we wanna move a curve according to v in the normal direction, that's obtained by moving phi up and down, whatever this formula tells us, and then we cut. So you want to go for t equal 5, do this for t equal 5, find the 0 level set, and you got the curve evolution. So everything now is in implicit form. We have functions defined on the plane, and by moving those functions, we are moving the 0 level set, and we are getting curve evolution. For example, we're getting active contours. Why is this so important? Let me just illustrate a couple of ideas which I think will help us to illustrate how important this is. So remember that sometimes when we deform a curve, the topology can change. I'm going to ask you, which was the curve motion that produces changes in topology, that might produce changes in topology? Is it the curvature motion? Is it the affine motion? Or is it the constant motion? We know that. And we know that it's the normal motion. The normal motion can change topology. Now, when the topology of a curve is changing, if you discretize the curve, it's very difficult to understand that this point, that was neighbor of this point, actually ended up here, and this one ended up there, and now they're not neighbors anymore. They were neighbors one step before, but because of topological change, they're not anymore, and numerical analysis is very complicated when those things happen, when neighboring things just stop being neighboring things. It's very, very complicated. Now, when we are in this phi function, so imagine that this gray is the phi, and basically the two planes, the two green, light green and dark green, are just at different times. You are cutting this phi function. The phi function is moving according to v gradient phi. And all what I have to do is cut and be surprised if there is a topological change. I don't have to worry about connectivities. No worry at all, because I'm working on a grid, as I'm going to show here. So I don't have to work with particles and discretize a curve and remember who is neighboring with whom and how the neighborhood is changing when there are topological changes. I don't have to do that. I'm basically working with phi defined on a grid, as we have it here. This is just another profile, and phi is changing. Phi t is v gradient phi, and that's it. So we discretize that the same way that we discretized before. It goes up, it goes down, and at some point you say, I want to know the state of the curve evolution right now. You just slice it. You look at every place where the current phi is equal to 0. You look at every coordinate or every coordinate here. If there is topological change or not, you don't have to be aware of that. And that's the beauty of this. And this is how the active contours that we talked at the end of the previous video is implemented with this, where v is that velocity of active contours. So v can be, in a simplified fashion, g curvature, where g was this inverse gradient of the image or some function that makes it stop. So you want to implement active contours, all what you have to do is phi t equal g curvature times the absolute value of the gradient. And we know that the curvature, previous slide, we can also compute as a function of phi. So everything is a function of this surface that is defined on the grid. And that's the beauty of the level sets. It simplifies the whole numerics. And with it, we can implement the curvature motion, constant motion. Constant motion is absolutely trivial. Let me write it here. Phi t equal gradient phi. So the gradient, you might discretize the same way that we talked before. The pixel on the right minus the pixel on the center, the pixel on the top minus the pixel on the center. Phi t, you discretize like phi at t plus 1 minus phi at t. Any type of time discretization. We are not discussing a lot of numerical analysis, but just relatively standard numerical analysis that you can use to implement smart numerical analysis, but relatively standard, instead of having to discretize a curve. Very, very simple equations for as complicated as we want curve evolutions, curve motions. And I prove this only for curves, happens the same for surfaces, and actually the formula is exactly the same formula, but phi is now a function in higher dimensions, so exactly the same formula. So now you have the tools to do active contours, and we're going to actually see more of active contours later this week in some of the future videos. But you know curve evolution, and you know how to implement curve evolution as well. And as I said, we're learning a lot of new material, and as I say, you can go back and recheck this video. The proofs are really, really two-line proofs with basic calculus and algebra from very relatively simple calculus and algebra, but you don't have to be aware of it. I just explained it to you during this video and during the previous videos. So we keep advancing, and I'm going to see you again in the next video. Thank you very much.